Hello everyone, welcome to our third class. In this time, I'm going to talk about preservative measures to the acetic paper. Of course, against the acetic paper, the current system for manufacturing of neutral paper has been established. However, there are countless papers made of acetic paper. As a conservation measure, what I want you to pay attention in relation to the situation of acetic paper, as mentioned in the previous newspaper article published in 1979, is a technique for neutralizing acids in a paper. What we call the deacidification techniques, which neutralize the acids from the paper, has been developed around the Western society. In Japan, since the 1980s, the issue of acetic paper has been discussed mainly in libraries, and the countermeasures have been reviewed. Of course, maintenance of the storage environment is important to control the degradation of acidity, but it is necessary to increase the lifespan by neutralizing the acidic substances in paper. Deacidification is a means of suppressing the degradation of acidic papers. The purpose of deacidification is to settle alkaline reserve in the paper to neutralize acids by reacting to alkali. This technique is effective in suppressing acidic degradation, but this is not intended to recover physical strength of paper. Therefore, it is most effective to use it as a preventive treatment to suppress natural aging in acidic papers where degradation has not yet progressed. Of course, not all paper needs deacidification. These figures are electron microscopy observation of calcium compounds accumulated in papers, in which 18th century paper contains calcium compounds, and in modern paper, calcium compounds are sometimes filled with fillers to make the paper smooth. The reason why historical papers are well preserved compared to the acetic papers is that fabrics were immersed in calcium-rich limestone, or fibers were beaten in water rich in these compounds to be fiberized during process of fermentation. As a result, alkaline substances such as calcium carbonates or magnesium carbonate are included in a dried paper sheet. Therefore, deacidification is not necessary for such kind of paper. Conversely, for low-quality acetic papers, deacidification is an essential process as a preservative measure against acidification. Let's take a look at the principle of deacidification. This is a schematic diagram of deacidification, and this can be divided into two ways. One is aqueous deacidification, and the other is non-aqueous deacidification. In aqueous deacidification, alkaline chemicals are dissolved in water, and in non-aqueous deacidification, the suspension solution that small particles immersed in organic solvents is prepared. There are four-step processes for deacidification. First, alkaline solutions penetrate into the fibers and swollen, and the alkaline ions are migrate into the fibers and act directly on the acidic compounds to neutralize them and make salts. But the aqueous deacidification differs from non-aqueous one because soluble acidic substances can be washed out of paper. The neutralized salts also contain non-soluble substances which accumulated in the fiber in the form of carbonate that do not react with other substances. And this neutralizes the acids that is approaching afterward to remove all hydrogen ions derived from acids. In other words, neutralization of acidic substances sufficiently react with alkali to remove all hydrogen ions derived from acids. And as a result, neutral salts that do not react with other substances as stable alkali reserve are accumulated in paper. This is the point of the paper deacidification. I will show you a short video cited from YouTube which explains the principle of deacidification.
Ziel der Massenbuchentsäuerung ist es, die zerstörerische Säure im Papier zu neutralisieren. Der erste Schritt ist die sorgfältige Auswahl des zu behandelnden Bibliotheks- oder Archivmaterials. Bei Ungewissheit hilft der Schnelltest mittels pH-Stift. Nach einer genauen Registrierung der Chargen werden die Bücher auf einen speziellen Wagen verladen und in die eigentliche Behandlungskammer geschoben. Zuerst wird ein Vakuum erzeugt. In diesem verdampft die Restfeuchtigkeit aus dem Papier. Mit dieser Vortrocknung wird verhindert, dass das wasserempfindliche Entsäuerungsreagenz vorab mit dem Wasser reagiert und wirkungslos verpufft. Die eigentliche Behandlungslösung wird unmittelbar vor der Anwendung gemischt. Sie besteht einerseits aus dem Entsäuerungsreagenz und andererseits aus einer Inertlösung, die als Lösungsmittel agiert und weder Papier noch Druckfarbe angreift. Dann wird die Kammer mit der Behandlungslösung geflutet und die Bücher für etwa 15 bis 20 Minuten darin getränkt. Die neutralisierenden Stoffe werden dabei ins Papier übertragen. Abschließend wird die Behandlungslösung wieder aus der Kammer gepumpt und erneut im Vakuum eine Trocknung durchgeführt. In sogenannten Rekonditionierungskammern wird dem Papier unter kontrollierten Bedingungen langsam die Feuchtigkeit wieder zugeführt. Damit wird eine Kette komplexer Reaktionen in Gang gesetzt, die sukzessive die vorhandenen Säuremoleküle neutralisiert. Ein Überhang der Entsäuerungssubstanz, die sogenannte alkalische Reserve, bleibt dann im Papier zurück.
There are almost 50 types of deacidification methods have been developed so far, so let's take a quick look at a few methods. First of all, it is necessary to check whether the target papers are in a state of acidification. So in the library, as you saw in the short video earlier, they use pH check pen that observe the changes in color, or use pH test paper by contacting the paper. As previously mentioned, the deacidification methods can be divided into aqueous deacidification and non-aqueous one. First of all, a specific method was proposed by William Burrough in the 1960s to neutralize acidic papers by immersing them into alkaline solutions. Burroughs' first deacidification treatment at the time was to use an alkaline solution obtained by dissolving calcium or magnesium hydroxide or their carbonate, which is still being employed in many libraries. Burrough chose calcium and magnesium compounds because they were also included in the old paper that was in a good condition. After neutralizing the acidic paper, then surplus alkaline substances remain in the paper. Preservation can be improved by neutralizing acids that invade from self-produced acidic substances, which drive by chemical reactions with moisture or oxygen in the atmosphere or external air pollutants in the future. This method is basically carried out manually and can deal with only small amount of paper. So if you have a book, disassemble the book first and immerse each paper in an aqueous alkaline solution, so you can remove the acid. After drying the paper, binding it again in a book. Basically, if the object is not in the state of a sheet of paper, it must be disassembled once, although it takes a long time to process, but it has sufficient deacidification effect. And because the paper is immersed in aqueous solution, it has a cleaning effect to remove discoloration product either. And the cost of materials such as calcium and magnesium carbonate is cheap. If the quantity is small and valuable, it is better to use this method. But it is difficult to deal with hundreds of thousands or millions of acetic papers. And of course, aqueous deacidification cannot be used for object that is weak in water. For example, water-soluble paints or ink should not be immersed in an aqueous solution. And it is easy to deform wrinkles by wetting. Because paper is wet during the process, there is a problem that deformation such as wrinkles is likely to occur if drying is not carefully carried out. Because of this, Burrow began to develop a new method, which was a spray-type deacidification treatment. Basically, the ingredients used do not change as in the case of immersion in an aqueous solution. A solution of calcium carbonate and magnesium carbonate is sprayed onto each page of the book. After that, dry the paper and straighten the wrinkles on the paper, and the work is completed. In this method, the book can be deacidified in the form of one volume of book without disassembling the binding of the book. And although it has the effect of deacidification, it is clearly less effective than the method of immersing in an aqueous solution. So, it is not suitable for mass deacidification. On the other hand, non-aqueous deacidification is a method that does not include any water and reacts in the form of a solution or gas containing organic solvents. So the bound books can be processed without disassembling, and papers vulnerable to water can be applied. One of the non-aqueous deacidification treatments currently being employed is the bookkeeper method. This is a method of dispersing magnesium oxide particles in a solvent called fluorohaptan and spraying the suspension solution onto a book page. Spraying the suspension solution on paper fibers and then vaporize only the solvent to settle the magnesium oxide particles on the paper. And magnesium oxide particles combine with moisture in the air to form magnesium hydroxide, which slowly neutralizes acid. In the bookkeeper method, the deacidification solution can be sprayed to paper using the hand spray, or a large amount of papers can be treated using a chamber. If the amount of paper is small, spray each page, but to process large volumes of book at once, it is processed by immersing them in a closed chamber. But the size of the object that can be processed in the chamber is limited, so large map or weak objects are subject to deacidification by hand spray. Numerous methods have been developed over the past 50 years for mass deacidification. For example, in the 1970s, the US Library of Congress used the DEZ method using diethyl zinc gas as a countermeasure for large amounts of acetic paper. As a principle, first, about 1,000 books are put in the chamber and made into a vacuum state. Then, when diethyl zinc is vaporized and penetrates into the paper, it reacts with moisture inside the paper like bookkeeper method, depositing zinc oxide, which is an alkaline substance, and neutralizing acid. Of course, this can also be processed in the binding state of the book. The problem is that it is difficult to manipulate this compound because it is combustible, and the problem that smell remains on the paper and it contributes to the discoloration of the paper has been pointed out, though it has stopped using it now. Then, in the 1980s, the Book Preservation Associates (BPA) method was developed. The name of the developed company is used as the product name. First, put the book in the chamber and vacuum it as same as DEZ method. Then, an ammonia solution is introduced as a solvent to adsorb ammonia gas onto the paper. After that, once the gas is discharged and vacuumed again, the excess ammonia gas is removed, and then the ethylene oxide is introduced. It reacts with ammonia and moisture adsorbed in the fiber to produce ethanol amine, which neutralizes the acids, and the alkali component remains. In this method, it can also be processed while storing books in a box, using the property of gas penetrating well as an advantage of mass deacidification. However, there is a problem that the brightness of the paper increases slightly, and the reaction of the chemical itself is a little dangerous. This BPA method is not highly evaluated as a deacidification treatment of acetic paper. In Japan, a dry ammonia oxidation ethylene method called EAE, which improves this BPA method, has been developed and used since 1999. This is the same method and principle with BPA, but it is improved that the reaction occurs more efficiently when the chamber is vacuum treated and then reacted with ethylene oxide gas using ammonia gas instead of ammonia solution. However, ammonia gas and ethylene oxide gas are harmful gases, so care must be taken in handling, and the reaction must be carried out in an airtight system, and eventually the emitted gas must be absorbed into the sulfuric acid to be treated. The purpose of this deacidification treatment is to maintain the physical strength of paper and extend its lifespan by neutralizing acid to prevent the cellulose chain of paper from being cut more than that by acetic substances. However, the acetic substances present in the paper are not the only factors of degradation of the paper, but the degradation caused by oxygen, light, and heat is compounded. In other words, acidification is a very large degradation factor for paper, and the acidification treatment technique is the way to solve such serious degradation factors, but it is not a means to solve all degradation factors. Besides, the acidification treatment has a great effect on suppressing the long-term degradation of paper, but it cannot recover physical strength of paper in a state that is extremely deteriorated and difficult to handle as book object. Therefore, it is also combined with technique to reinforce paper, as I introduced in last time in response to deacidification treatment. In any case, the deacidification treatment should be carried out as a preventive treatment before the paper becomes remarkably weak and cannot withstand future use. In this regard, what the Library of Congress holds as a standard for the deacidification of book is that, first of all, it should be completely deacidify the acetic paper. Second, enough alkali should be retained in the paper. And third, the paper should be able to at least triple its life compared to untreated paper. I will explain this later. And finally, book should not be damaged. Time has passed since the degradation problem of acetic paper emerged, but no method that is considered optimal to satisfy all of these conditions as a mass deacidification treatment has yet to be released. Nevertheless, let's look at the effect of the large amount of deacidification treatment currently being carried out. The paper without deacidification, indicated by red area, decreases the durability rapidly, but it can be expected to extend the life more than 3 times in the deacidified paper, indicated by green area. However, effect of deacidification varies depending on the quality of the paper. The less durable the paper is, the less effective it is, which means the cost effectiveness of treatment increases by processing deacidification before acidification becomes serious. Besides, even if it is a paper that has been deacidified, natural degradation of the paper proceeds due to factors other than acidification, so we can assume that the effect of deacidification treatment delays the vulnerability of the paper. Of course, paper lifespan can be extended further by eliminating the degradation factor other than acidification. For example, the rise in the temperature also promotes degradation. If paper deacidified by a bookkeeper method is stored in 5 degrees, it can extend life by 30 times more than it is stored at room temperature. Based on the above, each library should first consider whether books and documents should be deacidified in countermeasures for acidic paper. In other words, it is necessary to check the nature or specificity of the collection to determine whether the preservation of information is prioritized or whether the object itself should be preserved along with the recorded information. And the deacidification treatment that is currently commercially available, the characteristics and effects of each treatment are clear. As mentioned before, the main problem is that in aqueous deacidification treatment, the dimensions of the paper can be changed by the use of water, and wrinkles are likely to be deformed. As a countermeasure against such a problem, it can be said that the treatment method with non-aqueous gas is effective. However, there is a possibility of a smell due to volatilization of organic components from the paper after treatment, and the paper may be discolored accordingly. Furthermore, restrictions in terms of environmental protection are expected to increase in the selection of sorbents for dissolving alkaline substances. Although ozone-depleting substances are not used in sorbents, some sorbents have been reduced as greenhouse gas, such as fluoroheptane. Because of these flaws, no deacidification treatment method is applicable to all objects, but the best deacidification treatment effect can be expected by properly selecting object before treatment. Of course, it is necessary to fully grasp the characteristics and treatment effect of each treatment before treatment. So far, we have looked into the preservation and deacidification of acidic paper. Next, I would like to introduce about the preservation and repair of Japanese hanging scroll. Paper or silk is often used as a base support for calligraphy and painting, but leaving only one sheet is very vulnerable. In order to preserve and appreciate, for example, hanging scroll, a folding screen, a flat frame, or a sliding door have been mounted since ancient times for the purpose of repairing and reinforcing the object. This repair technique is called Soko, which was introduced from China and Korean Peninsula along with the introduction of Buddhism, and is said to have originally been the work of monks. By doing this, for example, things that can be rolled or folded like hanging scrolls can be put in a wooden storage box and stored compactly, and it is convenient to move around and hardly exposed to the air, so discoloration and oxidation of painting paper can be inhibited. Let me explain the process before and after the lining briefly. First of all, as an investigation before repair, the structure, materials, and degradation state of the work should be investigated, and the direction of repair should be established. The investigation of the painting paper is necessary to prepare same paper for subsequent repairs. By investigating the degradation state of the painting paper, the cause can be confirmed, and what to improve is judged. It is also important to investigate color materials when considering in painting. As an observation method, observation with the naked eye is basically carried out, but a different state can be observed by changing the direction of the visible light, such as front light, oblique light, and transmitted light, which is not indicated here. For example, with oblique light, the position and degree of a wrinkle running horizontally like this can be found on the painting paper. Infrared observation shows traces of ink hidden under the painting paper. As an object analysis, if the collecting a very small amount of fiber sample is allowed, fibers can be identified like this with a C-staining solution to make sure the species of fiber, and elements consist of the pigments can be identified by fluorescent X-ray analysis. Next, painting paper is disassembled from the hanging scroll, separating the mounting fabrics. The purpose of cleaning is to remove foreign substances such as dirt and stains to improve the appearance visually. From the perspective of preservation, because the contaminants can react with the painting paper to promote degradation or to induce mold and insect damage, it is important to remove them. As for the method, water is sprayed on the screen of the painting. Blotter, which refers to the paper absorbs water, is placed under the painting paper to remove dirt. This is wet cleaning, and dry cleaning uses brush to remove foreign substances when water cleaning is not able to carry out. Of course, these are decided after evaluating in advance whether they are effective or safe for the painting paper. Next, process for preventing peeling is carried out, and since the old paint layer is built up with natural aging, animal glue solution is applied to reinforcing it and to fix it to the painting paper. Most of Oriental paintings use paint, mixing powdery pigments and animal glue, so most of adhesives used for peeling prevention is same animal glue. In some cases, this treatment is carried out as a preventive reinforcement procedure as well as a treatment to attach the paint layer that is currently being filled up. Basically, it is done after cleaning, but depending on the degradation state of the paint layer, cleaning may not be tolerated. So in the case, peeling prevention may be performed 1 or 2 times each before and after cleaning. Let's move on to the process of removing the lining paper. This is an important process because it means removing all the lining paper and replacing it with new lining paper to physically support the painting paper. This is a typical traditional hanging scroll. East Asian countries share similar shape of scroll art. I think you might have already appreciated this kind of painting somewhere in the museums. Such a hanging scroll has been preserved using lining techniques cultivated over many years, not just stored in a state of the painting paper. This helps fully in appreciating the artworks, as well as in mechanical supporting the painting done on Japanese paper. This is a structure of disassembled hanging scroll seen from backside. You can see that bottom side is a painting paper, and generally 3 kinds of different lining papers are attached to the back side of the painting paper. First layer of the lining paper is called hadaurashi, which supports the painting paper directly. And last parts of the scroll are composed of silk for decorative reasons. Of course, painting is aged as years went by, and restoration treatment involving replacing the new lining paper is repeated in a cycle of about 50 years. During this period, the degradation of lined paintings has accelerated significantly on both painting and lining papers due to the lack of proper lining techniques or using degradation-inducing materials or mismanagement. And consequently, as adhesive strength between the painting paper and lining paper comes to weak, lining loses its original function of supporting the painting paper. As shown here, the wet method has been used for a long time, but when wheatstarch paste is swollen with a large amount of water and loosened, it is removed in such a way that the layer is broken. If the paint layer becomes wet for a long time, there is a risk that dirt will wash out and move. But if it is done safely, the burden on the painting paper will be reduced in a short period of time. On the other hand, the dry method is aimed at removing the fiber by giving a small amount of moisture to the paper and loosening the interfiber bond. However, the first lining paper is directly attached to the painting paper, so It is difficult and very time-consuming, taking a few months. However, this method is effective for those with vulnerable painting paper. After the lining paper is removed, the lining is newly performed. Replacement of lining in repair is the most important process to preserve the artwork. The important thing here is the choice of adhesives. Starch paste is used for attaching the first lining paper to the painting paper, but aged starch paste is used for other lining papers. Aged starch paste appeared since the Edo period, and this pre-starch paste is stored in a cold and dark place for more than 10 years. During that time, microbial activity of mold has significantly reduced the adhesive strength. Pinkish part is used except for the part of black mold. It is an essential material to make a hanging scroll that can be unrolled softly. Chemical glue was developed 60 years ago, but not sure about the safety and stability of new materials. Therefore, conservators use starch paste, which are guaranteed to be safe when repairing cultural property. I will show you a short video about the process of first lining using wheat starch glue. This video was created for my experiment to make paper samples in the laboratory.
いくもやるんだったらもう比率今回出たらそれでもう混ぜちゃって、攪拌してこせばいいと思います。
やってて焦げちゃう場合もある。
でも毎日はそこまで焦げ茶色くなってとかは安くてもいいんだったら安いって言ってもね
3万ぐらいか
いやなんかそのどういうふうに実験のその
あ、これって2回くらいやる。
ちょっと2回やっとくか。後ろのねこれをこうくるくるくるくるこうまとめるんです。で一瞬だけど大丈夫。
そうだね。
またもう一回やるから。水入れる前に一回ちょっとハケでこねる。ハケ臭いな。海苔がこうちょっと集まってくるようなとろみ。ちょっとこれね海苔がねちょっと少なめなんだよね。もうちょっと OK だよ。この透明になっていくじゃない紙が。でこれちょっとさ毛が繊維がちょっとももけてきてるのねこれ、今ハケでこうやったから、それも結構この食いつきよくなるからこの支持体に対して、よし 私今思ったんだけど、本当ブラウンティッシュの方がちょっと一回り大きいんだよね、の方がまあよくやるけど、まあ、今回はいいでしょう。外側真ん中ってもう絶対力入ってるけど、ここが意外と入りにくいから、こう外までこう撫でるような感じで、ちょっと隣にこう
After the lining is finished, the defective part in the painting paper should be compensated. Because rolled hang scroll is normally unrolled for exhibition, so repeating rolling and unrolling the scroll leads to wrinkles, and consequently painting paper will be ported, and damages often progress due to rubbing of the ported mountain. Besides, painting paper can partially be lost due to the malachite burning, which the copper originated paint is easily oxidized and insect damage. So the missing part is filled with similar or same Japanese paper used as a painting paper. By compensating the missing part with the same material, the sense of visual discomfort can be reduced, physical homogeneity of the whole paper can be maintained. There is also a technique in Japanese style book to paste Japanese paper that has been torn to match the shape of insect holes from the back of the missing part. In the case of repairing a document damaged by insect bites, it is generally necessary to cover each insect hole with a mending or lining the whole surface of the documents. Finally, the work for applying coloring to the compensated part and the original part in order to eliminate the visual sense of incongruity is carried out. This is called inpainting. For example, when repairing a painting as antiques, they are often supplemented the color, so that the damage itself is not known. Besides, Buddhist paintings, which are objects of worship, require the statue to be divine and splendid, and in some cases, the statue's expression was added to the original part to be arranged. Currently, it is based on the principle of preventive conservation remaining current status, so it is assumed that only the parts compensated are colored, and in principle, no supplementary or additional drawings are made to supplement the images or letters themselves. This is because inpainting is directly linked to the finish, and from the viewpoint of authenticity, especially in the case of paintings, it greatly influences the way of looking at the work. The biggest advantage of the repair by Soko is that a traditional method that uses only water, Japanese paper, animal glue, and starch paste, which are all natural material. Therefore, there are fewer elements that make paper less durable than acetic paper. Also, those materials can be easily removed by adding moisture, so which makes available to be repaired safely again in the future. Let's move on to the preservation environment for paper object. In order to ensure preservation in the sense that historical recording media will be handed down to the next generation, it is necessary to identify the object and degradation status of the vulnerable paper before preserving and repairing it. However, no matter how successfully the preservation and repair are completed, if the objects are left in a bad environment that promotes degradation, the degradation will proceed again. In that case, should the object be repaired frequently and repeatedly? I don't think so. this put a heavy burden on the object. Therefore, objects should be stored in a safe and stable environment and permanently cared to prevent degradation. However, library facilities presuppose the use of books, so they should be used in the environment where they are used, and there is a contradictory relationship between utilization and preservation. Exposing paper objects to the reading environment for use only promotes degradation. That is, if the books are stored in a stacked room, all you have to do is think about books. But in the environment of a reading room, users should be convenient to read books, so the probability of being exposed to various degradation factors in the reading room increases. For example, although light brightness is not particularly required in a stacked room as one of the environmental factors, but it is an essential element for reading. Also, considering the temperature of the reading room is kept at around 23 or 24 degrees. But considering the preservation of paper objects, it is ideal to have a lower temperature than that. However, simply storing the books in the stacked room will not allow users to freely read them. Therefore, it is necessary to ensure that books can be used for reading on the premise of proper preservation and environmental management. Therefore, it is most important to measure and collect basic information on environmental factors such as temperature, humidity, light, pollutants, and organisms that cause degradation in order to detect and deal with problems in the library storage environment only. Consequently, degradation occurring in the object can be delayed. Therefore, I would like to explain each of these factors from a conservation scientific perspective, focusing particularly on temperature and humidity in this time. So let's look at the problems caused by changes in temperature and humidity. If the degradation of a certain object is caused by a chemical reaction of the material, the higher the concentration of substances contributing to that reaction, the faster degradation occurs. In short, in an easy-to-understand example, the more moisture comes into contact with the metal, that is, the higher the humidity, the larger the area of contact with the metal, the corrosion reaction progresses faster. Similarly, when the acetic paper is placed at a higher humidity, acid hydrolysis progresses, and oxidation degradation progresses as the area in contact with oxygen increases. The higher the temperature, the faster these chemical reactions proceed. Heat refers to the energy possessed by an object as shown here. But temperature is an easy-to-understand numerical representation of the amount of heat possessed by the object. As a result, temperature is closely related to chemical reactions because higher temperatures contribute more energy. Conversely, simply keep the temperature and humidity as low as possible to reduce the probability of a chemical reaction. Therefore, low temperatures are clearly desirable to preserve the object in a good condition. However, it is not realistic to set the reading room below 10 degrees. So, instead of setting the temperature in the reading room to around 23 degrees in considering of a user, heat insulation should be increased by using an air conditioner to suppress the variation of the temperature to a small extent. If so, wouldn't it matter if the temperature is low at least in the stacked room where users don't often enter? However, it is never desirable to give a large temperature difference under constant humidity when paper objects are brought in or taken out for reading, assuming that they move between the reading room and the stacked room, because it causes dew condensation on the surface of the object. For example, if the reading room is set at 23 degrees and the book is brought from a stacked room about 10 degrees immediately, dew condensation occurs on the surface of the paper. Therefore, it is impossible to set the library to 0 degree or less and the reading room to 23 degrees. If it is a time capture such as long-term preservation without using object, there will be no problem if it is kept below the freezing temperature, but in order for users to read the book, they have to set the temperature around 23 degrees so that it is not painful for people to read the book. Let's move on to humidity. In the air where we are now, there is moisture everywhere, though invisible to the eye. Organic materials such as paper, wood, lacquer, and glue, excluding inorganic materials such as metal and stone, basically contain some moisture because they absorb moisture easily in the air. The problem is the paper object expands by absorbing water, and absorbed water promotes chemical reactions and causes degradation. Therefore, humidity control is necessary to slow down the degradation even a little. Humidity refers to the amount and proportion of water vapor contained in the atmosphere. As you may heard, absolute humidity and relative humidity are used. Absolute humidity is the amount of water contained per unit volume expressed in gram. According to this figure, 11.5 gram of water is contained for 1 cubic meter. Absolute humidity is simple to distinguish because it must be attached with gram. And relative humidity is attached with percentage. In the field of conservation science, relative humidity is often used, which is a percentage of the ratio of absolute humidity to saturated water vapor. In other words, what percentage of the water actually exists now compared to the maximum amount of water that can be contained in the air in this space. The maximum amount of water that can exist at each temperature is theoretically determined. For example, atmosphere at 25 degrees can contain up to about 23 grams of water in 1 cubic meter, in which 23 grams means the amount of saturated water vapor. If 11.5 grams of water exists as the absolute humidity in the current 1 cubic meter, what is the relative humidity as the percentage containing moisture? Answer will be 50%. In other words, relative humidity represents the degree of wetness of the air at the time. The relative humidity varies with temperature. Again, the amount of saturated water vapor is expressed by gram as the amount of water vapor that can enter the 1 cubic meter of the air. So, we can think that the amount of water vapor that can enter the 1 cubic meter of the air is limited. However, if the volume is kept constant and the temperature is raised, the movement of gas molecules becomes faster because it is hot, producing more thermal energy, and the volume of gas expands like this, so the amount of saturated water vapor increases. This figure shows that relative humidity varies with temperature, but the size of this container shows the amount of saturated water vapor that varies with temperature. And it can be seen that the higher the temperature, the greater the amount of saturated water vapor. The gray area represents the current amount of water vapor contained in the air. First, because 1 cubic meter of air at 30 degrees has 30.4 grams of saturated water vapor, if it currently contains 15.2 grams of water vapor, the relative humidity will be 50%. Next, when the temperature of this air drops to 23.1 degrees without changing the amount of water vapor from 15.2 grams, the amount of saturated water vapor becomes 20.3 grams, and the relative humidity becomes higher, 75%. Besides, when the temperature drops more, the amount of saturated water vapor becomes 15.2 grams at 18.4 degrees, and the relative humidity reaches 100%. So, dew condensation begins to occur on the surface at this point. As mentioned earlier, condensation occurs when the amount of moisture in the air exceeds the saturation range when an object is suddenly moved to an environment with different temperatures. In fact, if you move book object from one local library to another, the object will not be directly affected by changes in outdoor temperature of the library because they must have fact the borrowed books. However, it is necessary to adapt the object to the new environment like in the relay room for several days before unpacking because it will be affected a lot while traveling. This is called seasoning, and the Agency for Cultural Affairs in Japan also stipulates that a sufficient period of seasoning must be secured when unpacking items that have already been placed in humid environments and transported over long distances during the cold season. Therefore, it is necessary to be careful not to cause condensation by properly seasoning. Now, let's move on to the degradation problem that occurs when the temperature and humidity environment in the library is not appropriate. When comparing temperature and relative humidity conditions more negatively affect cultural properties, so more attention is required. The biggest problem with high humidity is the increased risk of mold growing. It depends on the type of mold and growing temperature, but it is important to be careful because if the relative humidity reaches 65% or more, mold can easily grow. This is moldy on top of the Japanese painting and contaminating the screen, and it uses animal glue as a nutrient, so if wrapped unattended, the paint layer will eventually fill up. This is also an example of mold growing on the surface of a book. In particular, many Japanese cultural properties use plant materials such as paper and wood. Such materials have the properties of absorbing and releasing moisture. And since they absorb moisture when humidity is high and release moisture when dry, the object expands and contracts depending on humidity. This character is called hygrometric. Here is a schematic diagram of cellulose molecules. In dry surroundings, cellulose chains attract each other through hydrogen bond expressed by bonding with oxygen and hydrogen, as you can see here in the diagram, like this. But when humidity increases, water molecules invade into cellulose chains. Then water molecules break hydrogen bonds between the cellulose chains and enter just between the hydroxyl groups in cellulose molecules and subside by establishing new hydrogen bonding. As a result, a phenomenon called swelling occurs because the cellulose molecules are spread out by water. Conversely, when paper is placed in a dry environment with low humidity, the reverse process occurs and the paper shrinks. So we can imagine that the paper swells by moisture absorption and shrinks by dehumidification. Because paper changes sensitively to changes in humidity, especially when the fluctuation of humidity increases, the paper makes a difference in contraction and expansion. As a result, paper warps and curls like this. Wrinkles are formed and destroyed in time. As for objects that deteriorate due to changes in object dimensions, the effect of temperature changes is not as significant as the effect of relative humidity changes. So it is especially necessary to control changes in humidity. In any case, high or low humidity is not good for the paper object. Next, I will introduce examples of the effect of temperature and humidity on paper permanence. This table shows that a man named Smith conducted an accelerated aging test on the paper and determined the degradation rate of the paper at each temperature and humidity. When value 1 is based on the degradation rate at 25 degrees and 50%, the relative ratio between the degradation rate at each temperature and humidity is calculated. So we can summarize to what extent the life of the paper changes relatively depending on the temperature and humidity conditions. Of course, this value naturally changes if the experimental conditions and the type of paper are different. In this table, it can be seen that under 50% constant conditions, if the temperature is lowered by 10 degrees, the lifespan changes 5 to 6 times. This means that paper that lasts 100 years will last nearly 600 years. Furthermore, if the humidity is lowered to 10% in that situation, lifespan will increase by 20 times and last 2000 years. This graph here shows the average monthly temperature of the Leiji Family Library located in Kyoto. In summer, the temperature ranges from 26 to 27 degrees, and in winter, it ranges from 5 degrees. But humidity data were not available, so let's assume that the humidity of the library is 50% constant. So each value indicates a relative ratio between the degradation rate calculated by monthly temperature data and the degradation rate at 25 degrees and 50% calculated by Smith. You can confirm that paper degradation usually occurs during summer and does not occur in winter. In fact, since the humidity in summer is higher than the standard of 50%, the degradation rate here will be higher, and the degradation rate in winter will be smaller, so the difference between the two will be greater. Now the results are assumed to be 50%, and it can be seen that during the high temperature period from June to September, degradation becomes remarkable, but during other periods, the degradation rate decreases with a decrease in temperature. Therefore, we can think of a conclusion that cooling in summer is meaningful in the sense of suppressing the rate of degradation, but heating in winter will have a negative effect on promoting paper degradation. Considering the rate of degradation, the lower the temperature, the better for preservation. In general, 25 to 27 degrees, 50 to 60% in summer, 20 to 24 degrees and 40 to 50% in winter are preferred in terms of hygiene standards for the indoor environment. This will be the standard for the temperature and humidity of a general reading room in a library. If the preservation of the collection is prioritized, the temperature may be set lower. However, in the case of a stacked room, if there is an extreme temperature difference between the reading room, condensation may occur on the surface of the object as mentioned earlier, and as a result, it becomes unbearable to use. Therefore, as shown in this graph, cooling in summer is good, but heating in winter needs to be reconsidered, even from the perspective of suppressing pests, fungi, and insects that usually stop their activities in winter are purposely activated by heating. Therefore, from the perspective of energy saving, it is possible to reconsider maintaining a constant temperature and humidity throughout the year. Let's change the topic. We will briefly look at the environmental factors focusing on temperature that affects the paper degradation. This graph shows the degradation conditions of books. The examination was conducted by the National Diet Library, Keio and Waseda universities in Japan, including Yale University in the US. The vertical axis shows the ratio of the samples surveyed every 10 years. That is, it represents the proportion of acidic papers. The graph shows that the degradation of books published during the 30 years around the 1890s was remarkable, and the pattern of change was consistent with the result of both Japan and the US. But the problem is the percentage of acidic papers. For example, in the 1890s, 88% of books are deteriorated in Yale, but in Japan, the ratio of the National Diet Library was 29%, Keio University was 33%, and Waseda University was 21%, indicating that the acidic problem was not very remarkable in Japan. If the degradation of acidic paper occurred only by acid hydrolysis reaction, the degradation should proceed on the area placed in an environment with high temperature and humidity. But compared to New York and Tokyo, Japan should have a higher annual average of temperature and humidity. This is contrary to the prediction of the survey result. This is probably because the US was rich at the time, and heating up in winter, I think it was heated to 25 degrees more or less, and humidity is not given. It is possible that the degradation has become severe due to over-drying conditions. At that time, Japan was full, so it was cool in the library. European countries seems to have a similar situation. I think there was such a difference in degradation. Since then, Japan has become rich, and now I'm worried about how high this mountain is located. That's it for me to finish the class. I introduced the most important parts of the topics related to paper conservation and degradation problem. If you want to know more about the topics, please don't hesitate to contact me. Thank you very much for your listening.